During the 1930s, a mathematician investigating the foundation of mathematics named Alonzo Church introduced a formal system of expressing computational logic. The system he created was called Lambda calculus. It wasn't until the 1960s when the system found its way through different disciplines. It became something more than a mathematical formalism and became an important concept in linguistics and computer science. So, before we dive into functional programming, let's introduce ourselves to the formalism that inspired it, which is lambda calculus. These concepts may seem strange at first, since it imagines a mathematical foundation beyond numbers, sets, and logic. You can skip this part of the video and it won't really affect your understanding of functional programming concepts, but in my opinion, understanding the concepts of this formalism will give you a better appreciation for functional programming. These are the expressions in the lambda calculus formalism. Uh, Let big lambda, that's what this character means, be the set of expressions. One, an expression can be a variable. For example, an expression that looks like x, that is a variable. And when we say that it is a member of the set big lambda right here, we're saying that this is a valid lambda expression. Another variable, for example, y, is a member of the set of lambda calculus expressions because it is a valid lambda calculus expression. Another form of lambda calculus expression is the abstraction. If x is a variable and this fancy m right here is a member of big lambda, then an expression of the form lambda dot m is a member of big lambda, meaning it is a member of the set of lambda expressions as well. What this means is that any lambda expression that you can imagine right here, as long as it takes this form, then it is also a valid lambda calculus expression. So since we know that a variable that looks like this, for example, is a valid lambda calculus expression, then we can generate this lambda calculus expression that looks like this, lambda x dot y. And since we know that this as well is a lambda calculus expression, then we know that lambda x dot y, for example, is also a valid lambda calculus expression. And finally, the last type right here is what we call an application. Any lambda calculus expression of the form mn right here is a member of big lambda, as long as each of these are valid lambda calculus expressions as well. So if you have two lambda calculus expressions, let's say you have lambda x dot x, and if you put it beside just y, the variable y, then it is a valid lambda calculus expressions as well. So let's take a look at these important precedence conventions. You might get confused if you read some lambda calculus expressions. Some people often omit parentheses or single parameterizations to write shorter expressions. These are a few lambda calculus conventions and sort of ways they shortcut how to write expressions. And you might wonder what these things mean. For example, if you ever see a lambda calculus expression that looks like this, m and then n and then L, for example, you have three lambda calculus expressions put side by side each other. What this means implicitly is that there is a parenthesis on the first two. What we say is that lambda calculus expressions, specifically applications, are left associative. Meaning, if you ever find something of this form, x y, and then lambda x dot x. For example, you have 3 lambda calculus expressions placed side by side each other, then it means that you imagine that the application looks like this. This is placed beside this, and it just so happens that the left side expression is also an application. Number 2, consecutive abstractions can be uncurried. Just disregard whatever that phrase means. What this means is that if you ever see strange lambda calculus expressions that look like this, for example, lambda xyz dot m, this is just a shorthand for writing the following lambda calculus expression: lambda x dot lambda y dot lambda z dot m. Because if you look at the slide before this, you'll notice that this is not part of the valid lambda calculus expressions, but it is some sort of shorthand for this one, which is in fact valid. If you notice, this is a lambda calculus expression because a lambda calculus expression is of the form lambda x or lambda variable dot m, and it just so happens that m right here looks like this other lambda calculus expression there. And finally, the body of an abstraction extends to the right. If you ever see a lambda calculus expression that looks like this, I think I showed an example of this a while ago, lambda x, m, and then n, meaning there are 2 expressions placed side by side in the body of an abstraction. By the way, we call the part of the expression inside an application to the right side of the dot the body of the application or the abstraction. If you ever see something like this, there is an imaginary parenthesis there, meaning that the body of this specific lambda calculus abstraction is another application. Okay, so if that's a bit confusing, it will make sense in a while. So lambda calculus defines 3 ways to reduce or simplify a lambda expression. We're going to go through them one by one, and this is sort of the most important concept of lambda calculus expressions, because reductions are a way to simplify and evaluate lambda expressions. And you'll learn later that these reductions are basically concepts that are eventually adapted to functional programming concepts. And as a functional programming language makes sense, you'll see what are its roots and where it comes from, and how parallel or how deeply rooted functional programming actually is to math. Let's start with the first reduction. We call this reduction an alpha equivalence. An alpha equivalence states that any bound variable has no inherent meaning and can be replaced by another variable. So if you're given a lambda calculus abstraction, lambda x dot x, in this case right here, this actually just has the same meaning as lambda y dot y. In the same way that mathematical expressions like x is equal to 0 plus x, this proposition has the same meaning as y is equal to 0 plus y. The name of the variable right here doesn't have an inherent meaning. And if you replace it with any other variable, as long as you uniformly replace that variable, then you do not change its meaning. It's very simple. A generalization of this would look like this. Given some lambda x dot m, this abstraction's bound variable is x right here. Another special terminology that I'm introducing, we call this special variable the bound variable. The bound variable is the variable that you can find immediately right after the lambda symbol in a lambda calculus abstraction. The idea here is that the bound variable x may appear somewhere in the body of the abstraction. And again, the body of the abstraction is the whole expression to the right of the dot right here. So An alpha equivalence basically shows that the name of the variable again has no inherent meaning. Therefore, you can replace this x right here with any variable name. So a concrete example would be a sort of complicated lambda calculus expression that may look like this. Lambda x dot x x y, for example. That is a valid lambda calculus expression. So the way you can alpha reduce this is to write it with different variables. And as long as the variables that you write is uniform or consistent with the previous version, then it means that they have entirely the same meaning. Lambda z dot zzu has the same meaning as lambda x dot xxy. And you can imagine here that the process that I'm doing is that I'm replacing x with z and I'm replacing y with u. Amazing. Beta reductions. Beta reductions state how to simplify abstractions. This process is similar to applying a function in the context of functional programming. For example, if we use the identity function that you see here, lambda x dot x, and then you apply it to some other lambda expression, which is y, you can beta reduce this into y. Now that may sound like gibberish right now, but when you beta reduce some general application mn, what you imagine is that you're applying this left-hand side of the application to the right-hand side of the application. And if you remember the patterns of lambda calculus expressions, lambda calculus applications always appear in pairs. So here's another concrete example. If you have the lambda calculus expression, and I'm going to give you a sort of complicated one right here, lambda u dot lambda v dot u v u, and then lambda x dot x. If you look at this lambda calculus expression, you might wonder which pattern does this follow? Which exact type of lambda calculus expression is it? And if you break this down, add some parentheses so that it would be more obvious, you'll notice that this is an application. And applications can be beta reduced. So the way you reduce a beta application or a beta reduction is by first looking at the left side or the expression being applied, and you copy the body of that abstraction. Now, an application can only be beta reduced if the left side is an abstraction. Another rule right here. So there are two conditions for you so that you can apply a beta reduction. First, the whole expression must be an application, and the next, the left side right here must be an abstraction. Okay, so how do we reduce this? So the left-hand side, you look at the body of this abstraction. Now, the body of this abstraction, again, is everything that is to the left of the dot. So that would include lambda v until uvu right here. So you copy that, lambda v dot uvu. So the bound variable for this specific abstraction is the variable u. And what you do is that you replace all instances of u in the body with the expression that you find in the right side. Meaning, every possible u that you can find in this body right here will be replaced with, again, the right-hand side of the application in this context, which is the lambda.x. So replacing all u's, you're going to get lambda v dot lambda x. Sorry, I think I forgot to copy something because this doesn't make sense. This is lambda x dot x actually. There you go. That's the correct one. I just copied the wrong expression. So this is the whole expression that you're gonna replace u with, lambda x dot x. So lambda v dot parenthesis lambda x dot x followed by v, and then since there's another u there, replace that again with lambda x dot x, giving you this whole new expression right here. And believe it or not, this one right here can still be beta reduced, but we're not gonna explore this example more. There are more examples for us to look at later, much more interesting ones. Next is an eta reduction, and an eta reduction is not that easy to describe. Eta reductions describe equivalencies that arise because of free variables. If x is a variable and does not appear free in M, then we can basically simplify a whole lambda expression that looks like that into this M right here. And it's not, it's kind of weird to explain this one because the idea here is that you are reducing some redundancies in the abstraction before you reduce it. The eta reductions characterize some higher level simplifications that are not always as obvious as the other reductions we have a while ago. But these reductions are not really that common. But let's look at an example just to illustrate this one so that we can understand what this specific eta reduction means. And the way I can show you that these two expressions are indeed equivalent to each other is by applying some beta reduction to the left-hand side, for example. If we look at the lambda expression, lambda x dot xy followed by r, for example. Oops, that's wrong. Let's rewind a little bit. The pattern that we had a while ago is that if ever you find a lambda x mx, then you can eta reduce this into just m itself, like that. The idea here is that if I replace this m right here with an arbitrary lambda calculus expression, in fact, if I give an example, let's say this is just a simple lambda calculus expression, which is a variable y. If you have lambda x dot yx, any expression that you apply this to, for example, I've already used m, I'm going to use n instead. Any expression that you apply this to will have the same effect as this one. So what I'm saying is that according to eta reduction, this expression right here should reduce to just y itself. So if ever you apply this one to an arbitrary lambda calculus expression, for example, you'll notice that you're gonna get the same value as when you apply y to n. Yeah, that's why I said it's kind of hard to explain. You can only explain this using examples. If you apply a beta reduction for this specific application, what you are gonna get is yx, but replacing all instances of x with n, right? That's the process of beta reduction. So you're gonna get the expression nx, and it is indeed equivalent Oops, that was all wrong. Again, beta reducing this one is replacing all instances of the bound variable, which in this case is x, with the expression to the right of the application. So it will be beta reduced into yn, which is again exactly equivalent to this one right here. So forgive me if this whole section of the lecture is a bit confusing. I think this whole section would only make sense if you finish the discussion on functional programming. And it wouldn't really make sense if I place this discussion after the functional programming part of the lecture, because it would lose its meaning, because the idea here is that you will see how functional programming was imagined, or how functional programming was based on mathematics. And I think the best way to convince you is to introduce lambda calculus and then introduce functional programming after that. And when you see the similarities between them, you'll see that a paradigm like functional programming is indeed one of the most purely mathematical paradigms out there. Okay, I'm not done with my lambda calculus rant, by the way. Let's look at an example of reduction right here. Anyway, if you have problems grasping this one, I mean, I don't really expect you to be experts of this topic, of this section right here immediately. You can actually skip this. Yeah, this is just some sort of strange introduction to functional programming. You can imagine it like that. But if you do give it a try anyway, I think you'll appreciate it more. So before I end this lambda calculus expression discussion, let's look at an example of reducing some complex lambda expression, which applies more than one reduction methods. So I have here an example of a sort of complicated lambda calculus expression. Lambda x dot lambda y dot xy, but followed by the same copy of itself. Lambda x, my x's and my lambdas are kind of hard to differentiate. Lambda x dot lambda y dot xy, right there. So how do we reduce this one? So the first thing we need to do is to look at the outermost level of this expression. What is this expression? Which pattern does this follow? So if you look at this, it is actually two expressions placed side by side each other. And if you go back to the types of lambda calculus expressions, this is an application. And it is the kind of application where the left-hand side is an abstraction, which means these two conditions right here tell us that we can beta reduce this whole expression. So to beta reduce this one, you imagine this left-hand side as the expression being applied and this one as the expression being passed or being parameterized. So if you remember the process of abstraction, what you do is you copy the body of the abstraction that you find at the left-hand side, and the body of the abstraction on the left-hand side is this one right here. The body again is everything to the right side of the first dot that you see. So the body is lambda y dot xy. And the next thing that you need to do is to replace all instances of the bound variable. The bound variable in this case is x. So you need to replace all instances of x in the body with this expression right here. So doing that, we're going to get lambda x dot y dot xy, and then followed by another y. This y right here, this is the y that you see right here. And again, this whole expression right here is what is replacing the x that you see right there. Again, the reason why you're replacing x is because it is the bound variable for the abstraction at the left side. Great. So are we done? No, we can still reduce this application or this expression itself, and it's not that obvious at first because what you're going to end up with after this beta reduction right here, from here to this one, you're going to end up with another abstraction. But the thing about this abstraction is that there is an expression inside its body, and it just so happens that that expression can still be reduced. What kind of expression is in the body? This expression is, if you look at this one, this expression is also an application, right? This body, because it is two expressions placed side by side each other. It just so happens that the left side is this one and the right side is just y. And since that is an application and the left side is also an abstraction, then it means you can reduce the body of this whole expression again. So to reduce the body again, I'm just going to copy the variable here because this is not included in the reduction process. We're just reducing the body. So reducing the body, we're going to get lambda x dot lambda y, right? Dot xy, and then apply this whole thing right here to y. I just copied it. Again, the process of reduction is to take the body and then replace all instances of the bound variable x with the instance y. So the instance of x right here will be replaced by the right hand side of the application, which just so happens to be y, meaning you're gonna get the expression lambda y dot y y. And copying this back right here, because this should be attached, you're gonna get the really strange expression lambda y dot yy. So are we done? Is this the final reduction? So you cannot reduce this even more, but I actually gave you a trick question. I actually tricked you a little bit here because this reduction is actually incorrect. The reason why it is incorrect is because although x and y appear on both lambda expressions right here, if you notice this y right here and this y, they appear on both of the expressions. This x right here also appears on the other lambda expression. Although they are the same variables, or they look like the same variables, they don't actually have the same meaning necessarily. The x and y variables inside the left lambda expression right here are bound to this lambda abstraction, while this x right here is bound to a different lambda abstraction, which is this one. The problem is that the x and y variables outside the left lambda expression, which is inside the right lambda expression, are free in this context. Meaning, if you look at the x variable right here, this x variable is not bound to this x variable right here, or this whole abstraction that you can find at the left side. Again, because that is a different x than this x. It just so happens that they have the same name. And what happened, although the process that we used to reduce this into lambda y dot yy, because we didn't differentiate between this y right here and this y right here, we lost whichever y this means and whichever y this means. For example, there's some sort of ambiguity because is this y the variable which was originally bound to the first abstraction, or is that the one bound to the right abstraction? So to avoid a confusion like this, and to avoid ending up with an ambiguous lambda calculus expression, it is advisable to apply an alpha equivalency to give them different names. And you have to do that before you start reducing them all together. So I'm gonna do it all again, but this time we're gonna do it correctly. Okay, so starting with the original expression that we had, which was lambda x dot lambda y dot xy, and then another copy of that, which is lambda x dot lambda y, and then another xy. So to avoid the ambiguity between this y and this y right here, for example, again, they are not necessarily the same variable. It just so happens that they have the same name. To avoid that, we can just change all of the x's and y's in this expression right here to different variables. If we do that, then we won't be confused between the variables in this side and the variables in this side. And to do that, we just apply an alpha equivalency, which is just as simple as replacing the variables with different variables in a uniform manner. So I'm just going to copy the first one, but the second one, I'm going to change all x's into u's and all y's into v. So I'm going to end up with a brand new looking expression, but actually it has the same meaning as the previous one. So what I ended up with is lambda x dot lambda y dot xy applied to lambda u dot lambda v dot uv. And if we're gonna do the same process again, first thing that we need to do is to beta reduce this application. And if we do that, I'm just gonna sort of skip this one a little bit. If we're gonna do this beta reduction first, we're gonna end up with lambda y dot lambda u dot v dot uv, and then finally y. And then after that, we beta reduce the body of this one. We're going to end up with lambda y, which is just copying this one to this one. What you're going to end up in the body will be lambda v dot yv. So you can remove again these parentheses right here because it doesn't actually introduce some ambiguity. So you're going to end up with the expression lambda y dot lambda v dot yv. And if you are a bit keen, you'll notice that this has the same meaning through alpha equivalency with the expression lambda x dot lambda y dot xy. Right? It has the same meaning because the y's are just replaced with x and the v's are just replaced with y's. Which is actually kind of an interesting quirk, where you started with two copies of this one, you ended up with just one of them. There is a supplemental topic for lambda calculus expressions, and I'm not even gonna attempt making a lecture on that, but there are lecture notes that I've written. It is very interesting though, although it's kind of strange. It is a topic on lambda calculus encodings where you can sort of see how the mathematician Alonzo Church sort of created lambda calculus as a basis for all of mathematics. You can see how lambda calculus creates numbers, how lambda calculus creates Boolean functions, and etc. It's a whole another rabbit hole, but uh, it's an interesting rabbit hole. Who knows? It's available for you if you are indeed interested in that.